Okay, this is the Math 601 video where we're going to completeness of inner product spaces and how that impacts Fourier series. Essentially, it's a prelude to Fourier series convergence. And in so doing, we need to talk about completeness. In completeness, we have to talk about Cauchy sequences, which are basically sequences that try to approximate something. So, a sequence in this works in a metric space, or a norm space. Those of you in my topology class know about metric spaces. Otherwise, you can just perfectly well do with norm spaces, as we talked about in the previous video. So a sequence in a norm space, let's give it a name, an, is Cauchy if for every epsilon greater than 0, there is an n such that the distance between not adjacent, but any terms following that are less than 0 for any m n greater than capital N. So the definition of Cauchy. Basically, the terms get closer and closer together. So the intuition is that the terms approach 1. Okay, well, let's see here. It seems like this is the perfect situation where limits exist. Well, first off, if I have a Cauchy sequence, does it mean there's a limit? Well, not necessarily, but the other way around is true. So if En goes to L has a limit, then An is Cauchy. So whenever you have a limit, it's a Cauchy sequence. Alright. The proof is not so hard to see. So first of all, we know this sequence has a limit, so we're going to make use of that. So if we want this to be Cauchy, let's see, we need to say, yes, there is, suppose, let epsilon be given. And what we should do is we should try to find an n. So let capital N be the n. So the n such that the distance between An minus L is less than epsilon for all n, epsilon over 2 for all n greater than n. Why did I use the epsilon over 2? Yes, because what I'm going to do is I'm going to simply say, then, if m and n are both bigger than capital N, well, what I'm going to do is I'm going to do the add 0 trick. I'm going to add 0. And then I'm going to use the triangle inequality. And then I'm going to make the observation that each of these are epsilon over 2, which is less than epsilon. Perfect. Alright, so Cauchy sequences show up whenever you have a sequence that has a limit, but the converse is not true. So, what we want to do is we want to know what we want to do is we want to be able to take a look at what happens in a sequence like this. What about a sequence like 1 over n for n obviously the sequence has a limit of 0. But if you're in a situation here, now this is a metric space comment, metric space might say that this thing is, well, going to what? Going to 0, but if we're in this interval, oh wait, this is not a vector space, so this is sort of a pre-counterexample. This is a failure in a metric space. But if in this guy here with the usual metric, this thing doesn't have a limit. The limit isn't in our set. Uh-oh. But as I said, I'm sort of cheating here. I'm not using norm spaces and whatnot. So what we really want to do is we really want to go after the situation where we've got a normed a vector space. Well, where would that work? So consider instead the rationals. The rationals, of course, well, they're a vector space. This is a vector space. Add any two rationals, I got a rational. Take any rational linear product. Switch vector space over rationals. It's still a rational, etc., etc. It's in fact a norm space. Norm just being the distance, and then take the difference, take the absolute value. That's a metric, and a norm. But this one's got some problems. You can very easily can cook up a sequence converging to an irrational number. Of course, it won't actually converge in this sequence, in this vector space, but it will be getting closer and closer together. So in fact, what we do when we think about the reals is we think about the reals are all the possible limit points of Cauchy sequences of the rationals. This is called the completion and completing. So here's a definition. In a vector space in which, or perhaps not in a, simply a vector space in which all Cauchy sequences converge is called complete. So for instance, the reals is complete, the rationals are not. Now why do we care about this? Well, we care about this because there are some sequences that we would like to deal with, in particular the Fourier series. So if we have a basis for an inner product space, and that basis is E1 up to En, well, if that's really a basis, then, well, first of all, they're all linearly independent. We know that from before. That's what it means to be a basis. Now suppose this set is orthonormal, which means, of course, that their inner products are all zeros, etc. Well, then what we want to do is we want to write f is equal to some ai's ei, 1 to n. And of course, the way we found this is the general Fourier trick. Inner product everything in sight. And here we go. ai e j e I. And we notice that because it's orthonormal, all of these terms except the I equals j term is going to be 0, and that I equals j term is going to have 1, so this says aj is that. So f is So that's the general Fourier series. Now this works great in a finite dimensional setting, but what about if n is not finite? Well, two bad things can happen. The first thing is that maybe this thing converges to something, and it ain't f. Oh, well, no, we know that's not going to happen. But what if it doesn't converge at all? That's sort of the first problem. And the second problem is, well, does it converge to f? Right. So, it converge at all? Does it converge to f? The first question is answered by completeness. The second answer is something called Parsifal's. So once we put those two things together, then we can say that it really does actually converge. But what does completeness have to say about the matter? Well, completeness has to say something about the matter in the following way. See, let's take a look at what happens about whether or not this thing is, if we're in a complete space, then we're in good shape. So if V is a complete inner product space, and this has a special name, complete inner product spaces are Hilbert spaces. Physicists will like that. And I do too. Hilbert spaces are very handy. So if you're in a complete inner product space, then all you need to show is the sequence is Cauchy. So when is it going to be Cauchy? Well, let's see here. We want to look at, I equals 1 to m, ei, f, ei, and we're going to take a look at, we want to know when does this sort of thing get small. We want to know when that's going to get small. Well, if you look at this here, you notice the following. Notice that this thing here is going to be equal to, let's take, without loss of generality, m being smaller. We go up from m to n. And let's see here. This can be bounded above using the triangle inequality. And hey, wait a moment here. This is an orthonormal basis. So those are all 1. You look at this using the Cauchy-Schwarz inequality. And you say, look at this, well, this doesn't look like this has got any hope of converging. Because you're going to go erase this guy and say, well, wait, this is equal to, m minus n, or n minus m, I guess, n minus m times. Oh, wait, this is not going to work, right? Fail. But if we focus our attention here, if this sum here converges as n goes to infinity, if this thing converges, and this is a pretty weak bound. If that converges, then we're in good shape. So the real focus in the whole Fourier convergence game is studying this term. If this is small enough, then we get convergence. Now, whether or not we converge to the right thing is as I said, this matter of Parsifal's theorem, which we'll also discuss with. So those 2 points need to be addressed when we talk about Fourier convergence. Whether or not each of these terms are going to 0, and whether or not we are successfully actually going to the right thing once we converge. Okay, well, hope you enjoy the weather, and we'll see you next time.